Okay, so we're going to do a lot of math in this unit, mole calculations. What we're going to be talking about here is Avogadro's number. Maybe some of you have heard it in the past. What a molar mass is, a molar volume, percent composition, and then we'll move on to empirical formulas. Avogadro's number. Recall, an atom's atomic mass is equal to the number of protons plus the number of neutrons in the atom. So when you look at periodic tables, you'll see the atomic number up here, the 6, and here's the atomic mass in atomic mass units. The unit for atomic mass is atomic mass units. Carbon-12 has 6 protons and 6 neutrons. One atomic mass unit, abbreviated AMU, is equal to 1/12 the mass of carbon-12, or approximately the mass of one proton or neutron. Protons and neutrons actually have slightly different masses, and that's why this symbol here is not the equal. That's kind of like approximately. That's what that means. What if you wanted to measure the mass of one atom in the laboratory? Would it be possible? Well, a single atom has a very small mass. One carbon atom has a mass of about 2 × 10⁻23 grams. So there's no way you could put one on a scale and measure it. Nothing we have is that accurate or goes to that layer of detail. Also, how would you trap the one atom and know that you had it? So basically we measure the mass through indirect methods, kind of like the Millikan oil drop experiment or through mass spectrometry. But you can't measure it directly. That's kind of silly. It would take a whole lot of atoms to give us enough material to directly measure in a lab. So let's start with hydrogen. It has a mass of 1 atomic mass unit, right? Just has 1 proton. How many atoms of hydrogen would be needed to make a 1 gram sample of hydrogen? This many. I'm not even going to try and read that. That's why we have scientific notation. And that number is 6.02 × 10⁻23rd. And is called Avogadro's number, or a mole. And you can click here. This is a nice video on how big a mole really is, and we're going to cover that in the next few slides in addition. The atomic mass of one carbon atom is 12.01 atomic mass units. Notice how it's not exactly 12, or 2 × 10⁻23rd grams. How many carbon atoms would it take to get 12.01 grams of carbon? And just notice the relationship we're setting up here. The same amount of AMU as grams, or at least the same numerical value. So here's our mass of one carbon atom. Here's the total mass we want. So we're going to say the mass of one carbon atom times the number of carbon atoms has to equal 12.01 grams. So we divide through by this guy, comes over here, and you see this, and we find out that we need 6.02 × 10⁻23rd atoms. And that will give us 12.01 grams of carbon. That number should look familiar to you already. That number, 6 × 10⁻23rd, is Avogadro's number, and it's related to the mole. So for example, 1 mole of pennies, which would be 6.02 × 10⁻23rd pennies, could be distributed to all of the currently living people of the world, so they could spend $1 million per hour, every hour, day and night, that's important, for the rest of their lives. 1 mole of marbles would cover the entire Earth, including the oceans, for a depth of 2 miles. If you were able to count at the rate of 1 million numbers a second, it would take about 20 billion years to count out 1 mole. And I'm pretty sure that's longer than the age of the universe. All right, so what are we saying? The mole's pretty big. But don't be scared of it just because it has a funny name. It's just a grouping of numbers, like dozen, ream, etc. A dozen means 12 of something. A mole means 6.02 × 10⁻23rd of something. So here's just a couple other quantities to make you feel more comfortable. Dozen is 12, gross is 144. A ream is 500. When you buy paper for your printer, you get a ream. It's got 500 pages in it. And a mole, 500 sheets, 2 pages per sheet. So 100 pages, 500 sheets. And a mole is 6.02 × 10⁻23rd.